When life did not begin on Earth. Life. It surrounds us, defines us, and yet remains one of the greatest unsolved mysteries in the history of science. For centuries, humanity believed that life on Earth was born here, forged from lightning, oceans, and ancient chemistry. But what if that belief is wrong? What if life did not begin on this planet at all? What if the seeds of biology came from the stars, drifting silently across the cosmos, waiting for the right world to awaken them? This is the unsettling, controversial, and deeply fascinating idea known as panspermia, a theory so radical that it challenges not only biology, but our place in the universe itself. Panspermia does not whisper its claims, it shakes the foundations of human understanding. It proposes that life is not rare, not fragile, and not confined to Earth. Instead, life may be a cosmic phenomenon, spreading, surviving, and evolving across planets, solar systems, and even galaxies. According to this theory, Earth is not life's birthplace, but merely one of its many destinations. A temporary harbor in a much larger biological journey that began long before our planet even existed. To understand why such a bold idea is even taken seriously, we must first confront an uncomfortable truth. Science still does not know how life began on Earth. Despite decades of research, countless experiments, and extraordinary technological advances, the origin of life remains elusive. We can describe life, manipulate it, even rewrite its genetic code, but we cannot recreate its first spark. The gap between non-living chemistry and living biology remains one of the most profound mysteries ever faced by science. The traditional explanation, known as abiogenesis, suggests that life emerged spontaneously from simple organic molecules in Earth's early oceans. In theory, under the right conditions, chemicals gradually assembled into complex self-replicating systems. But in practice, this process has proven staggeringly difficult to demonstrate. The leap from amino acids to DNA, from random chemistry to organized information, appears almost impossibly vast. Each year, new discoveries seem to deepen the mystery rather than solve it. This is where panspermia enters, not as a replacement for evolution, but as a relocation of life's starting point. It does not claim that life magically appeared. Instead, it asks a different question. What if life formed somewhere else first? Somewhere older, somewhere larger, somewhere with more time, more energy, and more opportunity than early Earth. The universe, after all, is unimaginably ancient and immense. Our planet is 4.5 billion years old, but the universe itself is nearly 14 billion years old. That difference matters. It means life could have emerged billions of years before Earth even formed. Entire civilizations of microbes could have risen, evolved, and spread long before our solar system ignited. In that context, Earth may simply be one stop in a cosmic chain reaction. The earliest form of panspermia dates back over 2,000 years. Ancient Greek philosopher Anaxagoras proposed that seeds of life existed throughout the universe, carried by cosmic forces and capable of generating life wherever conditions allowed. At the time, this was philosophy, not science, a poetic attempt to explain existence. But today, with modern astrophysics, microbiology, and planetary science, the idea has returned with unsettling credibility. In the 20th century, scientists like Svante Arrhenius revived panspermia in a more scientific form. Arrhenius suggested that microscopic life could travel between stars, propelled by radiation pressure. Though controversial, his proposal planted a seed, one that would later grow as space exploration revealed something astonishing. Life is far more resilient than anyone ever imagined. We once believed that life was fragile, easily destroyed by radiation, vacuum, extreme temperatures, or time. Space, we assumed, was lethal. But experiments shattered that assumption. Bacteria exposed to the vacuum of space survived. Spores endured intense radiation. Microorganisms frozen for tens of thousands of years reawakened. Some life forms proved capable of surviving conditions more extreme than anywhere on Earth's surface. Life, it seemed, was not delicate, it was stubborn. Then came the meteorites. In 1969, a meteorite fell near Murchison, Australia. When scientists analyzed it, they found something extraordinary. Complex organic molecules, including amino acids, the building blocks of life. Even more shocking, these molecules were not contamination from Earth. Their isotopic signatures proved they formed in space. This discovery transformed the conversation. If the ingredients of life are common in the cosmos, then the universe is not chemically hostile to biology, it is chemically prepared for it. Over time, dozens of meteorites were found to contain organic compounds, sugars, nucleobases, and complex carbon structures. Space was no longer an empty void, it was a chemical factory. Planets, comets, and asteroids appeared capable of delivering life's raw materials across vast distances. Suddenly, panspermia no longer sounded like science fiction. It sounded like a logical extension of what we were observing. But panspermia goes further. It suggests not just molecules, but actual life could travel between worlds. Microbes encased within rock, shielded from radiation, could survive interplanetary journeys lasting millions of years. Impacts powerful enough to eject rock from planets like Mars are known to occur, and we have Martian meteorites on Earth to prove it. If rocks can travel, why not life inside them? This raises a profound possibility. Life on Earth may be Martian in origin. Billions of years ago, Mars was warm, wet, and potentially more hospitable than Earth. If life emerged there first, meteor impacts could have carried microbial passengers to our planet, seeding Earth long before our oceans stabilized. In this scenario, Earth did not invent life, it inherited it. And Mars is just the beginning. Beyond our solar system lie trillions of planets. Many orbit stars older than our Sun. Some exist in environments vastly different from Earth. Worlds with thick atmospheres, powerful magnetic fields, or energy sources unknown to us. In such places, life may not only exist, but thrive on a scale we can barely comprehend. Over cosmic timescales, material from these worlds could spread, collide, and exchange biological information like a galactic ecosystem. If panspermia is true, then life is not an accident. It is not rare. It is not confined. Life becomes a cosmic process, emerging wherever physics and chemistry allow, then spreading relentlessly, adapting endlessly, surviving catastrophes that destroy planets and stars alike. In this view, the universe itself may be alive with potential, quietly cultivating biology across unimaginable distances. The implications are staggering. If life came from space, then we are not isolated. We are part of a much older story, one that began long before humanity, before Earth, perhaps before our galaxy itself. Our DNA may carry echoes of alien worlds. Our biology may be linked, at a molecular level, to life elsewhere in the universe. We may not be alone, not because aliens will visit us, but because they already did, billions of years ago, in the form of microscopic travelers riding ancient stones through the dark. Yet panspermia is not without controversy. Critics argue that it simply moves the problem elsewhere. If life did not begin on Earth, where did it begin? How did it start there? These questions remain unresolved, but supporters counter with a powerful point. Science often progresses not by answering every question at once, but by reframing them. Panspermia reframes the origin of life as a universal question, not a planetary one. And that reframing changes everything. Because if life is cosmic, then discovering it elsewhere is not extraordinary, it is inevitable. And if it is inevitable, then humanity's search for meaning, purpose, and connection takes on an entirely new dimension. We are not a fluke. We are not an exception. We may be the result of a universe that has been quietly creating life, spreading it, and watching it evolve for billions of years. And this brings us to the most unsettling question of all, a question we will explore next. If life travels through space, could intelligence travel with it too? Cosmic delivery systems. How life travels through space. If life truly did not begin on Earth, then one terrifyingly beautiful question follows naturally. How did it get here? Space is vast beyond human intuition. The distances between stars are not measured in kilometers, but in light years, distances so extreme that even our fastest spacecraft would take tens of thousands of years to reach the nearest star. For life to cross such emptiness, it would need more than luck. It would need a delivery system written into the mechanics of the universe itself. Surprisingly, the universe appears to have provided exactly that. Every planet, moon, and asteroid exists in a constant state of motion, collision, and exchange. Space is not static. It is violent, dynamic, and endlessly recycling matter. Asteroids crash into planets. Comets sweep through solar systems. Planets eject material into space during catastrophic impacts. Over billions of years, these processes form a vast, natural transportation network, one capable of carrying rocks, ice, and possibly life itself across astronomical distances. This is the foundation of lithopanspermia, the idea that life travels through space protected inside solid rock. When a large asteroid strikes a planet, the impact releases energy equivalent to millions of nuclear bombs. Such impacts are not rare in cosmic history, they are inevitable. Early Earth, Mars, and Venus were bombarded relentlessly during the solar system's youth. Under these conditions, chunks of planetary crust can be blasted into space at escape velocity. We know this is possible because we have found meteorites on Earth that originated on Mars. Their chemical signatures match Martian geology perfectly. These rocks traveled millions of kilometers, survived atmospheric entry, and landed intact. Now consider what that means. If rocks can survive such journeys, then microbes sealed deep within them could be shielded from radiation, extreme temperatures, and vacuum. Inside a rock just a few centimeters thick, radiation levels drop dramatically. Temperature becomes stable, time slows down. For a dormant microbe, space becomes less of a death sentence and more of a deep freeze, a suspended animation lasting millions of years. Laboratory experiments have shown that certain bacteria and spores can survive these exact conditions. Some microbes endure intense radiation doses that would kill humans instantly. Others survive dehydration so extreme that all metabolic activity halts, yet resumes once water returns. Life, it turns out, does not need comfort. It needs only opportunity. Mars, in particular, stands out as a prime candidate for early life. Billions of years ago, Mars had rivers, lakes, and possibly oceans. It had a thicker atmosphere and a magnetic field to protect its surface from radiation. At that time, Earth was still forming, its surface molten, its environment unstable. If life emerged early in our solar system, Mars may have been the better birthplace. Then came the impacts. Asteroids smashed into Mars, ejecting debris into space. Some of that debris eventually intersected Earth's orbit. Over millions of years, countless rocks could have made the journey, each one a tiny ark carrying dormant passengers. When those rocks struck Earth, the microbes inside would encounter warm oceans, stable chemistry, and a planet ready to host life. In this scenario, Earth did not invent life, it received it. But lithopanspermia is only one pathway. Another delivery system comes from the most spectacular travelers in the solar system, comets. These icy wanderers originate from the outer regions of solar systems, places rich in organic chemistry. Comets contain water, carbon compounds, amino acids, and complex organic molecules. When they approach stars, their ice vaporizes, releasing vast clouds of material into space. When they collide with planets, they deliver their contents directly to planetary surfaces. During Earth's early history, comets bombarded the planet heavily. Some scientists believe that a significant portion of Earth's water came from these impacts. If water can be delivered, then so can organic molecules, and potentially microbial life. Comets are not just dirty snowballs. They are chemical libraries, preserving the conditions of early solar systems for billions of years. Even more astonishing is the possibility of interstellar panspermia, life traveling not just between planets, but between stars. Stars form in clusters. In their early stages, solar systems are packed closely together. Material ejected from one system can easily drift into another. Over cosmic timescales, entire galaxies may exchange biological material. If life arises even once in such an environment, it could spread widely, seeding multiple worlds before those systems drift apart. Some scientists propose that dust grains themselves could carry life. Microscopic organisms, or even fragments of DNA, could attach to dust particles and be propelled by stellar radiation. Though controversial, this idea gains plausibility when we consider just how small and resilient life can be. At the molecular level, biology is not bulky, it is information encoded in chemistry. And information is remarkably durable. In 2020, scientists discovered phosphine in the clouds of Venus, a gas associated with biological processes on Earth. Though later debated, the discovery reignited interest in aerial life, organisms living not on surfaces, but suspended in atmospheres. If life can exist in such extreme environments, then the range of habitable zones expands dramatically. Space becomes less hostile, more accommodating. Another shocking discovery came from the International Space Station. Bacteria exposed directly to space survived longer than expected. Some even repaired radiation damage using mechanisms still not fully understood. Life was not just surviving space, it was adapting to it. This leads to a disturbing implication. Space may not be a barrier to life, but a medium for it. If life can survive impact ejection, interplanetary travel, radiation exposure, and atmospheric entry, then the universe becomes biologically connected. Planets are not isolated experiments. They are nodes in a vast cosmic network exchanging matter, chemistry, and possibly evolution itself. This raises an extraordinary question. Could evolution occur across planets? Imagine microbes traveling from world to world, adapting slightly each time they land. Over billions of years, this process could create a shared biological ancestry across multiple planets. Life in different solar systems might not be entirely alien. It could be distant cousins, shaped by different environments but rooted in the same ancient chemistry. This would explain something deeply puzzling: the apparent speed of life's emergence on Earth. Geological evidence suggests that life appeared almost as soon as Earth became habitable. That rapid emergence is difficult to explain through random chemistry alone. But if life arrived already functioning, already tested elsewhere, then the timeline makes sense. Earth may not have waited for life to form. It may have been infected by it. Yet critics argue that panspermia merely shifts the mystery. If life came from elsewhere, where did it originate? But this objection misses a crucial point. The universe offers vastly more opportunities for life to arise than a single planet ever could. With trillions of planets over billions of years, even extremely unlikely events become inevitable. Panspermia does not deny abiogenesis. It multiplies its chances. And as we explore the solar system, the evidence continues to tease us. Mars shows signs of ancient microbial activity. Europa and Enceladus hide oceans beneath their icy shells. Titan hosts complex organic chemistry unlike anything on Earth. Each discovery strengthens the idea that life is not rare, it is persistent. The more we look, the more we realize something unsettling. The universe seems prepared for life. Which brings us to the most controversial question of all, one that pushes panspermia beyond microbes and molecules. What if intelligence itself is part of this process? What if life does not just spread accidentally? What if, at some point, it learns to spread itself deliberately? Are we the evidence? Intelligence, aliens, and the final implications. If life can travel through space, then the final and most unsettling question becomes unavoidable. What happens when life becomes intelligent? Panspermia begins as a theory about microbes and molecules, but it does not end there. It stretches forward in time, forcing us to confront the possibility that intelligence itself may be a natural consequence of cosmic biology, not a rare accident, but an expected outcome. And if that is true, then humanity may not be discovering panspermia. We may be living proof of it. To understand why this idea is so disturbing, we must first understand what intelligence really is. Intelligence is not just thinking. It is information processing, pattern recognition, memory, prediction, and adaptation. These abilities do not appear suddenly. They evolve gradually, step by step, over immense spans of time. On Earth, intelligence emerged after billions of years of biological experimentation. But Earth may not have been the first laboratory where this experiment began. If life arrived here already billions of years old, already shaped by evolution elsewhere, then intelligence on Earth may be the continuation of a story that began on another world. This reframes humanity's origin in a radical way. We are used to thinking of ourselves as Earth-born, Earth-shaped, and Earth-bound. But panspermia suggests that our biological roots may extend far beyond this planet. Our DNA could be a cosmic artifact, carrying molecular memories from environments we have never seen. The fundamental chemistry of life may have been tested and refined across multiple worlds before ever reaching Earth. And this possibility becomes even more chilling when we consider how quickly intelligence arose once complex life appeared. In geological terms, humans emerged almost instantly. For billions of years, Earth hosted simple organisms. Then, suddenly, in a cosmic blink, intelligence appeared, capable of technology, language, and space travel. That speed is difficult to explain if intelligence is a rare fluke. But it makes sense if intelligence is a latent potential, waiting for the right conditions to activate. Which leads to a darker idea. What if intelligence is not just an outcome of panspermia? What if it is part of the mechanism? Some scientists and philosophers have proposed a concept known as directed panspermia, the idea that life may have been deliberately spread by an advanced civilization. Not as an act of conquest, but as an act of survival. A civilization facing extinction might choose to send its biology into the cosmos, encoded into microbes, spores, or synthetic life forms, designed to seed future worlds long after the civilization itself has vanished. In this scenario, life is not just accidental cargo. It is a message, a legacy. This idea was seriously discussed by scientists like Francis Crick, the co-discoverer of DNA. Crick acknowledged that the complexity of life seemed almost too ordered to arise quickly through random chemistry alone. Directed panspermia, while speculative, offered a way to explain life's rapid emergence without invoking supernatural explanations. And here is where the theory becomes truly unsettling. If directed panspermia occurred once, it could have occurred many times. Entire regions of the galaxy could have been seeded intentionally, creating clusters of biologically related worlds. Life on different planets might share biochemical similarities not by coincidence, but by design. The universe could be filled with distant cousins, life forms that evolved separately, yet share a common ancestral origin. This possibility forces us to rethink the search for extraterrestrial life. We often imagine aliens as fundamentally different, bizarre, incomprehensible beings. But panspermia suggests the opposite. Alien life may be disturbingly familiar. Carbon-based, DNA-like, built from the same molecular toolkit. The universe may not be filled with strangers, it may be filled with relatives. And that raises a haunting question. If intelligent life seeded the universe, where are they now? This is where panspermia collides with the Fermi paradox, the famous contradiction between the high probability of extraterrestrial life and the apparent silence of the cosmos. If life is common, and intelligence is inevitable, then the universe should be loud with activity. And yet, we see nothing. One possible answer is extinction. Intelligence may be powerful, but it is also dangerous. Civilizations may destroy themselves before mastering interstellar travel. In that case, directed panspermia becomes a kind of biological time capsule, a way for life to continue even when intelligence fails. Another possibility is even more disturbing. Advanced civilizations may choose not to reveal themselves. They may observe silently, or they may exist on timescales so vast that our brief technological moment barely registers. Or perhaps the most unsettling possibility of all is this: we are early. The universe is still young. Most stars that will ever exist have not even formed yet. Life may be spreading now, quietly, slowly, preparing the cosmos for intelligences that will emerge billions of years in the future. Humanity may be among the first to awaken, not the last. If that is true, then the responsibility is enormous. Because if panspermia is real, then life is not just something we possess. It is something we carry. As humanity develops space travel, we are already unintentionally spreading Earth life beyond our planet. Microbes cling to spacecraft. Spores survive sterilization. We may already be participating in panspermia, becoming agents in a process that began long before us. This raises profound ethical questions. Do we have the right to seed other worlds? Do we risk contaminating alien ecosystems, or becoming the alien invaders ourselves? Or is spreading life an unavoidable outcome of intelligence, a natural extension of evolution on a cosmic scale? Perhaps the most humbling implication of panspermia is this: life may be the universe's way of knowing itself. Through life, the universe observes, remembers, and reflects. Through intelligence, it asks questions about its own origin. In this view, humanity is not separate from the cosmos. We are a temporary expression of it, a thinking fragment of a much larger process that has been unfolding for billions of years. And so the theory of panspermia does not end with answers. It ends with perspective. It tells us that Earth may not be special because it created life, but because it received it. That humanity may not be unique because we are intelligent, but because we are aware. And that the universe may not be empty and indifferent, but quietly alive, patiently spreading the conditions for biology wherever it can. If panspermia is true, then the question is no longer, are we alone? The real question becomes far more unsettling. How many times has life already begun? And how many times will it begin again?